different functions for their given value. So if you could raise your hand if someone could give me the answer for number 1. Emily, what'd you get? 64, sure. We're just looking for f of 3, so we replace that x with 3. It's an exponent, 4 to the 3rd power. Absolutely, 64. All right, how about someone number 2? 125, absolutely. So replace your x with 2. Now notice that the little plus 1 is in the exponent. So we've got to add the 2 and the 1 in the exponent first. So we get 5 to the 3rd power, which Josephine told us, 125. Oh, number 3. Sarah. 26. Looks like today should probably go pretty smoothly. So this one, the plus 1, notice here the plus 1 was part of the exponent. Here the plus 1 comes after you evaluate your exponent. So we do 5 squared, and then we add 1 to that. It's 25 plus 1, 26. Last one? 106. So those are the two. 1. Anything to the 0 power is 1. And if 0 is the common wrong answer for that, and if you put 0 there, when you go to draw your graph, you should get this nice smooth curve. If you put 0, you get this big bump down that shouldn't be there. So anything to the 0 power is 1. And it follows from this rule. So when you divide like bases, what do you do with their exponents? Okay. And how about if I take anything divided by itself, what do I get? 1. So if I do 2 minus 2, it's x to the 0, but we know it's the same as 1. So that's why. The one other one that we should put on here, let's use that same f of x. So this last f of x is 6 to the x. How about if I wanted f of negative 2? So substitute in, I've got 6 to the negative 2nd power. Yeah, back to 10.2. So this is right from 10.2. Negative exponents, 1 over. So this is, it's not a negative number. Negative exponents never give negative numbers. We do the 1 over like we did in 10.2. So it's 1 over 36. Now, if you needed to graph this, 1 over 36 is a very, very small number. But when you need to graph, if you're not sure of your fraction, we talked about this before, grab your calculator, type in 1 divided by 36. Oh, I still have it up from the last class. 1 over 36, you'd be graphing approximately 0.03. Just a little bit above 0. So if you could do this, most of today is covered. That and plotting the points. So what we're going to do today is we're going to graph exponentials. So when we graphed quadratics on Wednesday, there was a lot of very specific information you needed. Not true for our exponentials. All we're going to do is we're going to choose a bunch of x's, we're going to plug those numbers in, get out our y's, plot our points. So with these graphs, it's always good to know what we're looking for in terms of a shape. So exponentials have this base b, and your variable is part of the exponent. This base has to be greater than 0, but it can't be 1. So this first graph, when your base number is greater than 1, so it's a number that's greater than 1, we have what's called an exponential growth. So your graph looks something like this. The left tail here flattens out. Even though it gets smaller and smaller, it's by a very little bit that it's going to continue to get smaller and smaller. And then it goes up like that. So if you hear something grows exponentially, it's because that tail shoots up on the right. What is the name of that graph called? It's exponential. So right here, exponential function. And this is a growth. Because it goes up. I guess I'm facing the other way, up like that. Now, if b, your base is between 0 and 1, which means it's a fraction, it's still an exponential graph, but it's just a decay. So it comes down the other way. So it's the smooth curve that we're looking for. Now, one of the things with our exponentials, we have to talk about domain and range. The domain is the same for all of them. So the domain for exponentials is the same for all of them. So a domain, we're always looking for our x values. So I want to see the span of x values. Or are there any x values I have to exclude? What do you think? Do I have any trouble areas? What's that? So domain is always x values. And what we're really looking for, are there any x values we have to exclude? So is it ever going to make this undefined? Not a real number, that sort of thing. Well, so if I'm looking at where this is going to the left, this graph is going to the left, it goes forever. But if I look how far it's going to the right, now it goes up, but notice it keeps extending out. So if this is going to get fatter and fatter this way, what number is it going to? Infinity. If it's going back all the way to the left forever, where's it starting? Negative infinity. Let's think about the graph on the right. So this time, the easiest tail to see, this one is going all the way to the right. So where's the domain going to? Infinity. Now, even though it slows down, this graph gets fatter and fatter and fatter and fatter as it goes back. So where's the left side going to? Negative infinity. The other thing is there's no x value that doesn't work. So we talked about trouble areas before with our domain. I don't have any of my trouble areas here, which means there's no values I have to exclude. So the domain on both of these, and this is for all of your exponentials actually, is again negative infinity to positive infinity. Any x value you substitute in for your exponent will give you back a real number. That's what we're talking about when we say negative infinity to positive infinity. Now, the range is going to vary. The range on these two graphs is actually the same. But we're going to flip to the end and look at the other pictures and talk about when the range is different. So on Monday, we discussed the range for quadratics. And the range is we're looking for the bottom of the graph, and then we're looking for the top of the graph. So one of the properties of exponentials is we want to look at basically where the tail looks like it's flattening out. What y value it looks like the tail's flattening out at. So if I look at this first graph right here, here's the tail. What value does it look like it's flattening out at? So that's the x value it's going to. But in terms of the y-axis, what value is it where this flattens out? 0. So it's getting really close to the x-axis, which has a y value of 0. So range is always y values. So this graph flattens out when y is 0. So that's where my range starts. That's where the bottom of the graph is. Emily? So it's not there yet, right? It didn't, my picture doesn't actually touch the line, right?
Yeah, but I thought like where the origin's at.
We don't need the 0.00, we're just looking at the y-axis.
Okay.
So domain covers the x,
Yeah.
and range covers the y.
Yeah.
So it's just the y value that's across from the graph, not necessarily what it's touching, but it's just across from it. So it's across from 0 on our y. So what we're looking for is we want to see where that tail flattens out, what number across from on our y-axis. So this one is across from 0. That's where the tail flattens out. But one of our properties of exponentials is it never actually reaches the value it looks like it's flattening out at. So I get these little numbers. I get this line really close when I use negative exponents. And the reason I get really close is when I put a negative exponent in, I get that 1 over, and that fraction gets smaller and smaller and smaller. So the numbers are getting smaller and smaller and smaller here, but there's no value for x I could substitute in that would make that 0. That would make this expression 0. Any negative exponent I put in is just going to make a smaller and smaller fraction. There's no number I could put in there that would make the whole expression 0. So the range starts at 0, but it never actually gets to 0. How could I show, we have some notation for this, as close as possible to 0 without actually touching? Molly? Parenthesis. So parenthesis means we never get to that value. We use the square bracket if we include it, but it's just a property of exponentials that whatever value it looks like we're approaching, we never get there. And then I want to look for the top of this graph. So where's the top of this graph going in terms of the y direction? Infinity. And then the same is true for this graph. The tail flattens out right at y equals 0, and it goes up to infinity. And we're actually going to flip to the last 3 problems, and then we'll come back and actually draw our graphs. So, oh, yep. What? The 0 to infinity?
Yeah, the range.
It 0 to infinity, yeah. Because the tail flattens out again at y equals 0. Let me show you one that has a different number and then see if you still have your question. So if I look at this first graph, down and find the domain and range. What's the domain? Negative infinity to positive infinity. Any x values work. For the range, what we're looking for is I want to see where it looks like the tail of this graph levels out in terms of a y value. So here's the tail of the graph. What y value is it across from? So, okay, so do we see how the tail comes down here and flattens out? I want to see what number this tail is across from. -3. I don't care where it crosses. There's a graph below that. I want to say, what does it look like the lowest value for this graph is?
Gotcha.
Yeah, -3?
Yeah.
Okay. So just we'll write these in a second. This tail right here, what graph does it level out at? Or sorry, what number does it level out at? 2. Okay. This one right here, what number does it level out at? 0. Okay. Yeah. Sorry. 0 goes right on the axis there. X-axis is 0. So if it gets to my x-axis, the y value there is 0 because we haven't gone up again. So we okay with finding like where the tail levels out? I'll show you in a sec. There's a kind of a trick to that.
I just got confused when you used the word tail.
Oh, the area that flattens out. So this range, what's the number it gets down to? -3. Exponentials never actually touch that value. Whatever value you think they're approaching, this is getting as close as, like, we wouldn't be able to see that it's not -3 if you were to look at it. But if you tried substituting in a number for x, you're never going to be able to get that function to work out to a -3.
Sense, though. It never touches it. We can't see it, but we'll just go with -3.
So the reason is, so if I have 2 to the x minus 3. So if I want this to actually touch -3, I've got to be able to make this first term 0. If I so to get small numbers, I use negative exponents because then I do 1 over. But I mean, even if I do 2 to the negative, it's a really small number, but it's not 0. So I can never get this first term to 0, which means I can never get this whole thing to just -3. Now, where's the top of this graph going? Infinity. So the flat part of this next graph, what y value does it line up with? 2. That's where our range starts. But we can never get there. Where's the top of this graph going? Top of the graph. Infinity. We're looking up and down for our range. What's our domain? Negative infinity to infinity. That's true for all of our exponentials. And the last one, domain? Negative infinity to positive infinity. And where did we say, what y value does this graph flatten out on? 0. I'll never be able to get there because I can't make an exponential 0. So we use a parenthesis. Now another place that can help you find range is if there's a big number added or subtracted on the end. So, -3, -3. +2, +2. This one has no number added on the end.
So it's 0?
Gives you the shift. That big number on the end gives you the shift up or down. What's that?
That's why I thought it was 1. So I looked at the plus one.
Oh, but it's part of the exponents. It's got to be the big number on the end. So questions on domain and range? Emily. What's that? Nope. Well, it's got an infinite number of numbers, but it's just the infinities for the domain. Yeah, it's just the range that will differ depending on if we move the graph up or down. So graphing these are not exciting. It's more monotonous than anything. To graph an exponential, you're just finding points and plotting them. And your homework tells you to use the points, the x values -2 to 2 inclusive, which means we're going to make a table. We're going to choose a bunch of x values. Your homework asks you specifically to do -2, -1, 0, 1, 2. Why do you hate it?
I just don't like tables. Tables just get me confused.
Well, then don't use a table. Don't put it into a table. If you don't put it into a table, do this. Do F. This is what I do in my table anyway. This is all we're doing. Over and over and over again. If you don't want to put it into a table, don't put it into a table. I don't care. But all we're going to do is take our function, 3 to the x plus 1, and evaluate it 5 separate times. Just like that little activity I gave you at the start of class. So f of -2, just going to substitute -2 in for x and evaluate. F of -1, we're going to substitute -1 in for x and evaluate. Again, it's not exciting. There's not different things happening. It's just the same thing 5 times. So what do I get for 3 to the -2nd power? 1 over 3 squared. So negative exponents, we just do 1 over 3 squared plus 1. And 1 over 3 squared? 1 over 9. So I'm looking at 1/9 plus 1. 1 and 1/9. Don't think about that too hard. You're adding a whole number to a fraction. It's just the whole number and the fraction next to each other. So 1/9 plus 1 is just 1 and 1/9. So if I were to write this as a point, because we're going to be plotting points, the x value, now if you didn't make a table, the x value is in the parentheses next to the function. So -2, and when I evaluate my function notation, 1 and 1/9. That's the point I'm going to be able to plot. And we're going to repeat. So what value did we substitute in?
Oh, shit, never mind.
-2.
Yeah, I gotcha.
So now we're going to do this again with a -1. How about 3 to the -1st power? 1 over 3 to the 1st power. 1 over 3. Plus 1. So 1/3 plus 1. 1 and 1/3. So my x value was -1. I worked it out and I got 1 and 1/3. That's my value. We're going to do it again. This time put 0 in for x. 3 to the 0 power. 1. Make sure anything to the 0 power is 1. So this is 1 plus 1. Look how easy today is. 2. We're going to do it again. This time we're going to use 1. So 3 to the 1st power is 3 plus 1 is 4. And f of 2, 3 squared plus 1, 9 plus 1, 10. 2. It's not a lot of steps though. It's the same steps over and over and over. Same thing. And it's something we've done before, so.
Can we do for the rest of the semester?
It can, absolutely. So now let's just plot these points and get our curve. So -2, 1 and 1/9, a little bit above 1. So -2 and then just a little bit above 1. And then -1, 1 and 1/3, so 1 and 1/3 is a little bit higher than that. It can be hard to show on your graph, but try to get that next point maybe just a little bit higher. I can't really show a whole lot of difference with the fat pen. And then we get into our integers. They're easier to graph. So 0, 2, over 0, up 2. And then 1, 4, over 1, up 4. And then over 2, up 10. Now you got to be careful when you connect these. You can see our curve in there. You can see our exponential curve, but you got to be careful with where is the left part, the tail flattening out. What number is that? Is this graph going to kind of flatten out at? 1. How do we know it's 1?
Well, it looks like it, but...
Yeah, but I can keep going. Oh, plus 1. Yeah, sorry, the last number in the function. Yeah, plus 1 on the end. That tells you what number it's going to end at. What number it's going to level out at. Plus 1. So when you connect this, just make sure that when you come down over here, you don't go below 1. So let's get... I mean, this tail technically is getting just like a little bit smaller, a little bit smaller, a little bit smaller, but it's approaching 1. So domain for this graph we know. -infinity to a positive infinity. How about the range? What value do I start at? 1. Not including 1. Never get there, so use a parenthesis. And then up to infinity. Questions? Now, on the next set of directions, it gives you 2 different functions and asks you to graph f of x, g of x, and then talk about how one is shifted from the other. I'm more concerned in this unit with you being able to graph and identify domain and range. So we might not even get time to talk about how one's shifted, but be able to graph and say the domain and range. So the homework wants you to graph 2 graphs on one set of coordinates there, but if you don't get to the shift part, that's okay. So what we need to do here is we need a table for f of x, or just a list if you're not into tables, and one for g of x. So the directions say to choose integers -2 to 2 inclusive for x. That's a fancy way of saying x values are -2, -1, 0, 1, 2. So don't let that part throw you off. That's all those directions say. And then I'm going to start with f of x equals 2 to the x. And then 5 times we're going to evaluate that function. So for the -2nd power, be careful with the negative exponents. I have 2 to the -2nd power. And how do I deal with negative exponents? 1 over. So I have 1 over 2 squared, which gives me 1/4. So if I'm going to write this as a point, because I do plot points, -2, 1/4. And then again, evaluate f of -1. 2 to the -1st power gives me 1 over 2 to the 1st power, which is just 1/2. I guess work on the other point. All right, so what do we get for f of 0? 0, yeah, it works out to be 1. So 2 to the 0 power is 1. 0, 1. And f of 1, 2 to the first is 2. And f of 2, 2 squared is 4. F of 3 fits if you want another point for overachieving. Sometimes they don't fit. Like, we're not going to actually be able to fit g of 2 on this graph. But let's plot. So negative 2, 1/4. Negative 1. Oops, I'm up 1 too high. Let's try this again. Negative 2, 1/4 is just above 0. Negative 1, 1/2. Halfway between 1 and 0. 0, 1. 1, 2, and 2, 4. So we can see our curve start to come out. Again, if you plot that extra point, if you plot 3, 8, you'll get a better idea of where is this going up. What number does this graph level out at? 0. So there's no big number added to the end, so it levels out at 0, which is the x-axis. And now we've got to do the same thing 5 more times for g of x. So make another table or another list. This time g of x is 2 to the x plus 2. Same 5 numbers. Substitute them in to find your y values. And this is another question that you typically find on the final exam. They like to have you graph stuff. So for exponentials, it's just keep plugging the numbers back in. And when you have the number added or subtracted in the exponent, you've got to take care of that first. So this is 2 to the 0 power 1. So my point is negative 2, 1. And then for g of negative 1, I have 2 to the negative 1 plus 2. Again, all the numbers in the exponent you've got to simplify first. It's 2 to the first, or 2. Then for 0, g of 0, 2 to the 0 plus 2 is 2 squared, 4. G of 1, 2 to the 1 plus 3, sorry, 1 plus 2. Getting ahead of myself, 2 to the third, which is 8. And this last one actually won't fit on the grid that I gave you. You do 2 to the 2 plus 2, it's 2 to the 4th, 16. So are there any questions just on finding the points? Or any of the values that we got finding the points? So I'm going to go ahead and I'm going to use a different color. Plot them on the same graph. So negative 2, 1. No fractions is nice. Negative 1, 2, 0, 4, 1, 8, 2, 16 would just be up a little bit further. Question though, what value is this graph approaching for my range? Where do I have to level this out? What value am I going to level this out at? 0. It's 0 again because there's nothing added or subtracted on the end here. So this is actually going to come down about as far as the other graph, or as far as the other graph. Now the question about the shift is, and this isn't one that I'm going to ask you, but if you look at the points on the graph in blue is always 2 to the left. Every point is 2 units to the left of the graph in black. But what I'm concerned with, again, you being able to find your points, plot them, and tell me domain and range. So your homework